Well, thank you, everyone. Good afternoon, and thanks for coming to this talk, where I'm going to talk about the 3 generations of big data processing. This talk is divided in 5 sections. Firstly, I will comment the characteristics of the big data environment and why we need 3 different processing paradigms. Then I will comment the difference between them, and I will also highlight the main milestones in terms of technologies and research publication of each one. Then section 2, 3, and 4, I will outline some technologies we can use for each processing paradigm. But it's not the goal of this talk to go in depth of this technology, but to classify the technology according to the processing paradigm and according to the step in the data pipeline that more or less is the same for all the processing paradigms. And finally, some conclusions about my talk. But firstly, let me introduce a little bit myself and my company. My name is RUBÉN Casado, and I come from the academic world. I obtained my bachelor and master degree in computer science at the University of Oviedo. Then I started working as teaching assistant and researcher in the same university. I focused my research in software quality in distributed systems and advanced transaction models. And finally, I obtained my PhD in software engineering. During my career, I have worked also in Oxford Bruce University in UK and in INRIA Laureatine at France. And now I'm working in the Trilogic company when I'm the responsible of the research line about big data. Well, Trilogic is a Spanish IT company. It's located in Asturias and Madrid. And the main feature of our company is that we really love innovation and research. We are about 100 people working there, and currently about 25% of the people is working in the development and research department. We work in different domains, including healthcare, transport, safety and security, innovation management, and so on. This bet for the innovation allows us to reach the international market, even being a small or medium company. The kernel of our research model is the research projects, because the research projects allow us to work with many important people and to address realistic issues in different domains. We started with small internal projects, then we moved to regional and national projects, and now we are focused on international projects. In fact, we are very proud of our international projects. We are involved in 7 ongoing FP7 projects, where we are the coordinator of 5 of them, and also we are the coordinator of 5 Eurostar projects. To sum up, in Trilogic, we love research and innovation, and due to our expertise in different domains and different international projects, where we have to deal with huge amount of data, different data processing models, we realized that the big data technologies that are quite new were so useful for us. And although these technologies were going to be more useful in the future, so we took the decision to create a specific team in Trilogic that we call Data Adopter, specifically focused on big data technologies. Well, once I have finished the presentation, let's start talking about the big data processing. But what is big data? We usually define big data as a large amount of structured and unstructured data that cannot be managed by the classical software system based on relational databases. And we say that this kind of software cannot manage the information due to one of these 3 popular features: volume, that refers to the huge amount of data that we now have to deal with; velocity, that refers not only to the frequency of the data generation, but also to the need to achieve results with low latency in real time; and variety, that refers to the different source and datascape that now we are using. So we have 3 problems: volume, velocity, and variety. But there are 3 solutions. 2 of them, batch processing and real-time processing, are regarding to the data processing that is the goal of our talk. Well, batch processing is the solution to manage large amount of data. We say that this processing paradigm works with static data because the information is already in the system. So the main goal of the batch processing system is the scalability. If your data set grows up, your software solution has to get bigger. So in order to achieve this scalability, the batch processing system uses a parallel distributed approach. Probably all of you know Hadoop. That is the standard technology for batch processing. And this kind of system achieves fault-tolerant architecture, but the batch jobs takes a long time to finish, so it's not suitable for requirements where you need low latency. An example of a batch processing system is to analyze the web log of a website in order to identify the customer buying patterns. On the other hand, we have the velocity problem. We need a way to manage streaming data with low latency, and this is the goal of the second processing paradigm, the real-time processing. Basically, the idea is similar to the batch processing. They use a parallel distributed fault-tolerant approach. But in order to achieve low latency, real-time processing systems use a smaller data set that are stored in memory instead of disk. A classic example of real-time processing is to identify the trending topics in Twitter. OK, we have seen two different processing models, batch processing for large amount of data, and real-time processing for streaming data. But what about the system that requires to manage large static data, but also have to take into account the new information that can arrive as streaming data? This is a new processing model that is called hybrid computation model that basically has to combine the result coming from the batch processing and the real-time processing. This is a high-level architecture of the hybrid computation model. It is based on the Lambda architecture defined by Nathan Marth. And basically, this model defines three layers: batch, real-time, and combination. When new information arrives, the data is duplicated and go to batch and real layers, both of them. The batch layer is processing the whole data set in a loop. But since a batch job can take a long time to finish, the new information is not analyzed yet. So in order to mitigate or to compensate this delay, the real-time layer only processes the information that has not been analyzed yet by the batch layer. Okay, both layers store the partial results in a database, and then there is a combination layer that gets the result coming from the two different databases and achieve in real time the final results. Well, these three processing paradigms refers to a different big data generation. The first one is batch processing. The inception of this first generation was 2003, when Google published the papers about the Google file system and the MapReduce framework. But on those days, not many companies had to deal with big data problems. So we say that the first generation started in 2006 when Hadoop was born. The second generation is the real-time processing. Some companies, like Twitter and Yahoo, realized that they had to deal not only with big static data, but also with big streaming data. This generation started in 2010 when Yahoo created the first technology that it's S4. But this second generation is still open. Just a couple of months ago, Google has published a paper about how they deal with the streaming data, and LinkedIn has open sourced a new technology for the same goal. And the third generation is the hybrid computation model. The inception of this third generation is the definition of the Lambda architecture by Nathan Marth in 2012. But it's too early to say that we have started this third generation, although there are some promising technologies, as we will see later. Well, this is the timeline of 10 years of big data processing technologies. As I said, the first generation started in 2003 when Google published some papers. In 2005, Doug Cotin started working in an open source version of the Google's idea. Then he moved to Yahoo, and Yahoo liked the idea, the Hadoop project. And in 2008, Yahoo open sourced a reliable version of the Google's ideas. In the following years, other companies like Facebook and Yahoo worked on abstraction layer on top of the MapReduce framework, and they created Hive and Pig. And the second technology started in 2010 when S4 is created by LinkedIn. But a main milestone in the second generation is the creation of Storm. Storm was developed by Nathan Marth and open sourced by Twitter. Well, as we can see here, we are still in this second generation because LinkedIn has presented SAMSA a couple of months ago, And Google has published the mile-well fault-tolerant stream processing and internet scale. Really interesting paper about how Google deals with streaming data. And regarding the third technology, we are in the inception, we are in the very beginning with the definition of the land architecture. Well, we have to use always these 4 steps in a processing pipeline. No matter what processing paradigm you are going to use, you always have to get the information, store the data maybe permanently or maybe temporarily, and to analyze the information in order to get some results. So in the rest of the talk, we will classify the technologies taking into account these steps. And in the rest of my talk, I will use this example that is a real project that we are executing at DataAdopter. The main goal of this project is to capture, analyze, and store information coming from the air quality system in Asturias. So Asturias is a region in the north of Spain with about 1 million people, and they have about 100 static stations and a lot of mobile sensors sending information continuous about the air quality. This is an example of the data that they send, basically station ID, the number, where the sensor is, and different measures about the component of the air. Well, in this, also the government of Asturias have stored all the information, all the measures from more than 10 years. In this project, we found the 3 processing paradigms. We need batch processing to analyze the large amount of static data. We need real-time processing to monitor in live the status of the air quality in Asturias, getting information from the sensors. And also we need a hybrid computation model because we need to make prediction, taking into account the historical behavior, but also the current status. Well, let's briefly talk about the batch processing technologies. As I said before, we will classify in terms of these 4 steps. So let's start with data acquisition tools. The first technology is a really easy technology, is the Hadoop file system commands. Really easy to use, but quite interesting if you have to manage your own cluster. Basically, this tool allows you to move information from a source to the Hadoop cluster. Here is an example of how we move our air quality system that is stored in our Linux system to the Hadoop system. Another more interesting technology is Scoop. Scoop allows getting information that is stored in relational databases. So Scoop is compatible with almost all SQL language database, so it's quite easy to integrate in your system. But Scoop not only allows importing data, but also exporting the data. So in order to use Scoop, you have to define, firstly, what do you want to do, import or export, what data are you going to move, and the data connections. Pretty easy to use. Well, Flume is another very important technology that was developed by Cloudera. Well, we can use Flume for different tasks, as we will see later, but now we are going to see Flume as a data acquisition tool. The main goal of Flume is to move information from a source to a data storage system. For example, the Hadoop file system. The main difference between Flume and the previous technology is that we can use Flume to get streaming data. The architecture of Flume is quite simple. There are 3 different elements: source, that are in charge of reading the new information; sink, that are the elements that write information to the final destination, for example, the Hadoop file system; and channel, that temporarily store the information until the data is consumed by the sink. For example, in our air quality system, we can use Flume for moving the information that is generated by the static station to our cluster for further analysis. Scribe is another technology for data acquisition in batch processing that was developed by Facebook. From a high-level point of view, it's quite similar to Flume. We can see Scribe as a collection of processes running on different machines and waiting for new information. You can push information in terms of message and the category of the message. And then you define how do you want to work with different categories. There is a central scribe node that receives all the information coming from the scribe nodes and finally write the information to the final destination. As I said, it's quite similar from a high-level point of view to a script. So we can use in the same way we use Flume. In this case, we are using Scribe to get the information coming from the sensor. So we define the category of the message that is mobile. We create a new message that basically is to read a line from a sensor log. Then we create a client, send the message, and the information is already in our Scribe system. Well, it's time to go about data storage technologies. In batch processing, the most important one is the Hadoop file system. Probably all of you know how it works. Basically, it describes a master-slave architecture where the information is stored in the data nodes, and there is a name node that manages all the nodes. In order to achieve better reliability and better performance, the information is split into blocks of the same size, and these blocks are replicated in different data nodes. Another different way of storing information in Hadoop is HBase. HBase is a NoSQL database inspired by the Google's Big Table. And the main feature of HBase is that allow random real-time read-write access to the data, which is quite important for some kind of process. But you have taken account that it's not a classical database. So for example, you cannot use SQL to access to the data. Well, now we are going to talk about the data analytics tool, maybe the most interesting one. In batch processing, the most important one is MapReduce. All of you already know how it works. Well, as I said before, in order to achieve scalability, you need to use a distributed parallel approach. And developing parallel code was becoming really challenging for the developers. And this is why MapReduce came into the picture. MapReduce is a framework for developing parallel code using just two functions, map and reduce. Map split the input information into a smaller process in terms of key value, and reduce basically generate the solution for a specific key. Even with this simple programming model, we can define different design patterns, including join, sorter, filtering, and any type of static function. And we use MapReduce in our air quality system in order to obtain the sulfur dioxide average of each station. We have the sulfur dioxide is one of the measures we obtain coming from the sensors. The map function basically creates a key value tuple with each element, where the key is the station ID, the value is the measure of the sulfur dioxide of this station. Reduce is very easy. They receive all values from the same station, just sum up all elements and divide by the total number of elements. And we obtain some result, something like this. Well, MapReduce is a strong framework for developing big data application, but sometimes it's not easy to think a real solution in terms of map and reduce terms. It's not friendly, and it's not a friendly way to program. So to deal with this problem, there are abstraction layers on top of MapReduce framework. One of these technologies is Hive, that was developed by Facebook. The main feature of Facebook is that allow using SQL language. So for example, you can integrate your business intelligence application in a big data platform. On the other hand, you have to know that all instructions that you write in Hive have to be translated into MapReduce jobs. That is worse than writing your native MapReduce. And in addition, SQL is not always the best way to address some data analytics problem. For example, it's not easy to develop data meaning or machine learning algorithms. But it's quite easy to use. We can use this Hive in our system. Firstly, we have to create the table and load the information in the Hive metastore. And then it's just to execute this SQL sentence that is really simple. Well, Pig is another technology on top of the MapReduce framework. It was developed by Yahoo. Hive uses SQL, that is a declarative language, and Pig uses a procedural language, Pig Latin. But the ideas are quite similar. So we can use Pig for doing the same. But it's really similar. Firstly, we load the information. Then we group the information by the station. And then for each group, we generate the average. Quite easy to use. Well, cascading is another open source technology that is developed by Concurrent, and it's another abstraction layer on top of the MapReduce framework. And they use a similar approach to pig, but cascading is more complex. So you can define more complex workflows using cascading than using Hive or pig. But on the other hand, writing cascading programs is a little bit more complicated, and a little bit more complicated to maintain the code. As an example, this is the same goal of the previous example, but you can see that now we have more lines of code to do exactly the same. Well, now we start a different branch of technologies. Spark is not an abstraction layer on top of the MapReduce framework, and Spark is not a modified version of Hadoop. Spark has its own engine that uses an in-memory process that achieves better performance than Hadoop. Spark is really useful if you need an iterative process. For example, if you define a workflow in MapReduce, once a job finished, it has to write the results to the disk. The next job in the workflow has to read the information from the disk. These input and output activities waste time. And Spark avoids these input and output time activities, because the information is stored in memory. So it's really faster than the Hadoop family. And Shark is it's basically the same idea that Hive for MapReduce, but Shark is the same for Spark. Basically, it's a way to use SQL on top of Spark. Well, to sum up the Spark family, we can say that the Spark ecosystem is faster than the Hadoop ecosystem because they use an in-memory processing approach. But on the other hand, they are novel technologies, so they are not have been tested in realistic, extremely large cluster. And you can find some performance problem if your information doesn't fit in the cluster memory. Well, let's move to the second processing paradigm, the real time. We will use the 4 steps. So firstly, let's start with data acquisition. Well, for data acquisition, we can use Flume in the same way we have used Flume for batch processing. Now, the only difference is you have to connect the Flume architecture to a temporal storage system like Kafka instead of the Hadoop file system. The data storage system in real-time processing are different from the ones used in the batch processing. The main goal of this storage is to temporarily store the information until the new data is processed by the data analytics tool. One of these technologies is Kafka, that was developed by LinkedIn. Basically, Kafka is a produce-consumer architecture where the information is classified by a topic. We can use Kafka in our air quality system in order to temporarily store the information that is coming from the mobile sensors. Pretty easy to use. We define a producer that basically reads the information in the sensor log, and then we send information with the topic to the Kafka system. On the other hand, we have the consumer. We define the consumer. We define which element we want, which topic of message we are going to work with, and we obtain an iterator to go through all the message of this system, this streaming. Well, Kestrel is another technology for data storage in real-time processing. From a high-level point of view, it's quite similar to Kafka. Kestrel basically is a distributed message queue that was developed by Twitter. If we have to compare Kafka and Kestrel, I will say that Kestrel is easier, but Kafka is better. I prefer Kafka. Well, now we are going to talk about the data analytics tools in streaming processing, in real-time processing. And the first one is Flume, a technology that we already know we can use for data acquisition. But Flume allows developers also to do some simple processing analytics thanks to the interceptors. Interceptors are intelligent systems that include some business application and basically allow users to modify, to filter the information based on some criteria, including the source, the time, data, and the content. So for example, we can use Flume to get the information only by the station number 2. So we drop all the information. And we have seen before, there is a field with the station ID. So we have to implement the business logic of our idea. That is quite easy because there are some Java interface to do that. And then we have to configure Flume to say that we want to use this interceptor. Well, but if you want to do a strong real-time processing, you need a Storm. Okay, Storm is the Hadoop for real-time. Storm was developed by Nathan Mart and open source by Twitter, and is defined as distributed unscalable real-time computation system. The architecture is simple. There are two types of elements: the spode that are in charge of reading the information from the source, and the bolts that process the information. The bolts get the information that coming from the spodes, but also from other bolts. So you can connect different bolts and create a topology. A topology is something similar to a MapReduce job. The main difference between a topology and a MapReduce job is that a topology never ends, because we are working with streaming data. So there are always new data to process. We can use, actually, we use Storm for calculating real time the average values of all our components. The first step is to define the topology. We have an spode that reads information from the sensor. The spode sends information, the message, to the line processor, which create a key value tuple with where the key is each component of the air, and the value is the measure of this value. And then this first bolt sends all the information with the same key to the same average value bolt that only have to calculate the average. Once we have defined the topology, well, the code is really easy. We create the topology, we define which is the spode, the first bolt, the second fold, and also we define that all tuples with the same key go to the same bolt. The next step is to develop the spotted bolts. It's not too difficult to develop, because there are some code you can use, and there are interface provided by the Storm that's not so difficult to do. Well, Trident is another technology that is on top of the Storm framework. Something similar to Hive or Pig, but for real-time processing. Trident is quite powerful, and it's really easy to use, but the built-in function is quite limited. And also, using Trident, you get worse performance than using Trident. So you have to balance if you want to go. You need good performance or an easy way to develop a streaming process. And S4 is another technology for real-time that was developed by Yahoo. Actually, this was the first technology for real-time processing. From a high-level point of view, S4 and Storm are the same. Of course, they are not the same. They use different programming model, and they use different recovery mechanisms. But in terms of our talk, how we can use the technologies, both of them are for real-time analytics. So in the same way we use Storm, we can use S4 to calculate the average of all the values of the air components here. And finally, we have Spark for streaming. That is more or less the same idea that Spark for batch processing. Actually, the programming model, the API, is quite similar. That's something that I really like of Spark streaming. It was the first approach to using the same programming model, address different processing paradigms. University of Berkeley claims that Spark streaming is faster than Hive, Storm and S4, but we had the same problem that we have with Spark for batch processing. It's a novel technology, so have in mind that maybe it's not so reliable. And finally, the hybrid computation model. Well, we are in the very beginning of this third generation of big data processing. In our opinion, it's one of the main issues that the research community have to address in the next year in the field of big data processing. Actually, more or less, we know what we have to do. We know we have to follow the Lambda architecture, and what we need is an abstraction layer on top of this theoretical model. We need some technology to make easier the development of hybrid computation model. And there are some promising technologies, Summenbird and Landup. Summenbird was open source a couple of months ago. It's being developed by Twitter. And basically, Summenbird is a library to write MapReduce jobs that you can execute in batch processing using Hadoop, in real-time processing using Storm, or even in a hybrid computation model using both platforms. This is more or less the high-level architecture of Summenbird. There is some kind of batch processing layer using Hadoop. some kind of real-time processing layer using Storm, and a merge. Here we have a combination layer to merge the results. Well, I like Hummingbird because it was the first approach with the same programming model to address the 3 different processing paradigms. But on the other hand, I don't like Hummingbird because this programming model is MapReduce. And as we have commented, MapReduce is not always the best approach to think about a solution. It's not easy to think in terms of MapReduce function. Another promising technology is Landup that we are doing in Data Adopter. Basically, Landup is an abstraction layer on top of many open source technologies that are needed for develop a whole Lambda architecture. Landup provides a simple programming model that is not MapReduce. It's an easier one, more friendly, for the 3 processing paradigm. It uses a cascading peak similar approach. So for batch processing, it's quite similar to those technologies. For the same programming model you can use for real time, and you have more built-in function than using Trident, and of course it's quite easier. And also using the same programming model, you can develop hybrid computation system. This is an overview of a Landup process. The information is represented as data object, no matter if it is streaming data or it is static data. Then you define the operations you want to apply to the data, and this sequence of operations is a workflow. Well, the operations are intelligent elements. Depending on what type of workflow you are defining, static, batch processing, real-time, or hybrid computation workflow, the operation already now have to deal with the information. So let's see some example of Landup code that we use in our high-quality system. This is an example of Landup code for batch processing. Firstly, we get the information. In this case, is static data from the historical store. We create a workflow. Then we define which operation we want to apply to the data. In this case, filter, select, group, and average. We include the operation in a workflow. And then finally, we execute the workflow in order to get the results. Pretty easy. This is a Landup code for real-time processing. If you can see, the code is quite similar. It's almost the same code. Now we are working with streaming data, so we are real-time processing. But the idea is the same. We define a workflow, we define which operation we want to apply to the data, include the operation in the workflow, and then we run the workflow in order to obtain live results. And this is an example of a hybrid computation model using Landup. As you can see again, the code is quite similar. It's almost the same. In this case, we are working with static data. We are also working with streaming data. We define the data, we define the workflow, and the same. The operations, include the operation in the workflow, run, and obtain the result. Pretty simple, pretty easy to develop all elements. Well, Landup is quite nice because it provides the same programming model for all the processing paradigm. And this programming model is not MapReduce. That is not so friendly for some people. On the other hand, Landup is an ongoing project, so it's not open source yet, and it has not been tested in realistic, extremely large clusters. We hope we can realize as open source in the incoming months. Well, to conclude, the main conclusion of my talk is that big data is not only Hadoop. Batch processing is the most common processing paradigm, but it's not the only one. So, firstly, identify the requirement of your system in order to detect which processing paradigm you have to use. Once you know which processing paradigm you need, then analyze the different alternatives you can use, which different technologies you can use in each pipeline step. Because it will be better. It's not always using the same technologies that other companies are using. So please have in mind this. And regarding the technologies, Hadoop is the winner of the big generation, of course. But it's quite important to have a look to the Spark and Shark ecosystem because they are faster in some kind of process. Regarding the second generation, the real-time processing, this battle is open. Let's see what Storm maybe is the most important technology, but let's see what's happening in the future if somebody open source a version based on the Google's ideas. And about the hybrid computation model, we are in the very beginning of this third generation, so stay tuned about the evolution of some technologies like Bird or lambda. And that's all. Thanks for your attention.
Thank you, Ruben. Questions? Oh, over there. Okay.
Yes, I can see someone on the top of the room.
Yeah. The mic is getting there almost.
Hello.
Hi.
Hello, very interesting, the lambda technology. I have a question about where do you consolidate the data? I imagine that data from the batch layer and from the real-time layer have to be consolidated in some database. Are you using HBase for that, or?
Yes, well, actually we are testing different technologies, but HBase, in our opinion, is one of the best approach for combining information coming from different approach. But also we have tested MongoDB, that is quite nice. So we are still in this phase of trying different technologies.
Okay, any more questions? Okay.
Hi, thank you for your talk. How easy is to include or use user-defined functions in these real-time streaming systems and in the hybrid computation models you presented?
Yes, this goal is one of the first things we thought when we took the decision of create a framework. Our idea was to provide to the end user a set of built-in functions to use. But of course, we know that we cannot provide all functions because each concrete project needs concrete functions. So it's quite easy. Lambda provides interface to include new user-defined functions. So it's not too bad. You have to implement 3 different interfaces, if I remember, okay, to include your new function in the Lambda engine.
Okay, one more question over here.
Hello. You just said that you are using Kafka to store data.
Mm-hmm.
Could you please explain this a little bit more? Are you using Kafka as a data store?
No, just temporarily. We use Kafka as a temporary data store for Storm. We process the information using Storm, but we need to store temporary information that coming from many sensors that is not possible to process all in real time using Storm. So it's like a help for Storm.
Have you found any problem when using Kafka?
No yet. No yet, but maybe in the future.
What would you say you lose when not using any more MapReduce?
What? In my opinion, anything, nothing. I don't like MapReduce. Of course, it's a very good framework for developing distributed software. It was a very nice idea. But my point of view is as a developer. I'm not used to work thinking in MapReduce or divide and conquer ideas. I used to study this kind of algorithm when I was young in the university. But in my opinion, it's not the best way to address realistic problems. And if we want people that used to work Java, general programming language, we don't have to change their mind to develop new application. In the same way that the new SQL database is moving to more similar to SQL databases, at least the language to manage the data, we have to think about new model of programming, but close to big data process, but close to the people that are really developing software. We don't have to create new people to develop software. We have to move to teach the new people, but using more or less the same processing approach. Yeah.
And in LabDup, what are you following some paradigm, or you just put any function you think you need, or how is that working?
Well, the processing paradigm is inspired by the one used for by Catalog, and also it's quite similar for the use in MongoDB for the aggregation framework. This is more or less the same idea. And if I understand your question about which functions are already included in the Landup, well, we use the more generic functions coming from the SQL world, but also the function that we have need in the development of many projects that we have execute. So it's a mix of between what we think people need and what we already have need.
Mm-hmm. And will you allow, if you end up the project and open sourcing, etc., do you plan to integrate some modules for third party to integrate their own functions?
Yes, actually, what we like to do is to integrate data analytics, something like Mahout and this kind of machine learning libraries from other people, because we are not data scientists. So it's not easy for us for developing specific functions to extract value from the data. So we are working on international research project about how to implement this new machine learning for streaming and something like that.
Thank you.
Okay, any more questions? Okay, then thank you very much, Ruben.
Well, just a last question. Well, this is the website. Well, it was in the slides. If anyone has more questions or is interested in Landup on collaboration, please email me, and it's well a pleasure for us to work with any of you. Okay.
Thank you, Ruben.